Hi everyone, so my name is Jonathan and I'm from Quantum Machines, and we're here with Mike from Equal One. And Mike will show us the Equal One system. This is a full quantum computer that you can see in this small rack, powered from a single power output, as Mike will explain, and controlled and powered by Quantum Machines control instruments. So Mike, maybe you can tell us a little bit about this thing that we're seeing over here.
So this is our Bell computer server, and it contains the full cryostat, cooling the quantum structure. We have a silicon-germanium 6-qubit design inside this cryostat, soon to be upgraded to 17 qubits. And it contains a cooler cryostat, GM cooler, which takes the temperature down to 4 Kelvin. And then inside we have a dual sorption helium-4, helium-3 cooler, which takes it down to 300 millikelvin. And that seems to be a very good sweet spot for operating quantum devices, spin devices. So this whole thing fits inside a single server rack case. This can be located in any location that has access to a 110 outlet, 16 amps, and can go into a data server room, IT server room, in somebody's office, and it's ideal for putting into, say, academic environments where they don't necessarily have full access to a big cryo lab with, a large investment of cryo equipment with helium reclamation facilities. This is a fully self-contained instrument. On top of the cryostat, we have instrumentation that is running spin qubit measurements, and there's reflectometry measurements are being measured by the QM OPX, and on the screen here we've got a charge stability diagram showing running live at this point in the show. And we actually had to bring the server, the computer, down from San Carlos in California down to the show in APS now. We had to cool it down before we actually left.
That's quite incredible.
And we had to then drive it down I-5, avoiding the potholes, and then roll it in, completely running all the time. And you can see here the transition line here from 4.0 to 3.1. That has not shifted at all in the last 5 days. So we're very proud of the stability of this thing.
And Mike, how many qubits do you plan to fit into this?
Well, 6 qubits right now, and 17 by the end of the year. We have plans for 50 qubits. And so we're intending to scale this up using silicon-germanium as a spin qubits is very scalable process and can be used to scale up to very large densities.
So what we see over here, basically, on top of the fridge, as Mike said, is the control electronics from Quantum Machines. There are 3 different devices here that are used to control the qubits. We have the QDAC, which is an ultra-stable, low-noise voltage source that I assume is connected to the gate electrode that are
biasing. That's right.
Those
we're balancing the well voltages very carefully. Each well has a separate control DAC output to control its potential, and then we have other for the barrier voltages. We have separate connections to control those.
I see.
Yes.
So essentially, to complement the stability of the qubits, which you have mentioned, and it's very impressive achievement. You also need a very low noise and very stable DC voltages.
Oh, definitely, most definitely, yes. So a lot of attention to noise and ground loops is needed to get the quality of measurement that we require.
Yeah, which is quite incredible that you can just power it from a single outlet with a...
Yes. And the noise didn't get any worse. It's the same noise figure that we did before we set off on our journey.
Nice.
So
And a lot of there is another layer of control, which is the RF control. I see that you said that you're using both for reflectometry, but also for qubit control.
Oh yes. There's a microwave pulsing that we're applying 10 gigahertz around that to control the qubit phase.
I see. So just to explain, so we see here the OPX. The OPX is the QM's flagship controller. And essentially on top of that, we have the Octave, which is an up conversion solution that goes together with the OPX. And the OPX can apply RF signals to the readout resonator, to the reflectometry circuit, which is then being modulated on board. So you can pick up the signals, you can do a feedback based on that. And the Octave is the up conversion for frequencies at the gigahertz range, which essentially go then, I guess, to some kind of like a feed line, an antenna line. That is used to do like spin resonant control type of.
That's right.
Yes.
Qubits.
All right. Incredible. Mike, anything else you would like to add on the system?
Well, the system also comes with a monitor at the back. I should open I'm not sure if this is visible.
So. But we see the same. The monitor shows the same thing.
Yeah.
Oh, okay.
So it comes with a display at the back, so you can access.
Nice. So the display is for what type of like graphical user interface are you having?
It's to provide direct access when you don't want any internet offline access. So for applications where maybe secrecy, privacy is an issue, that would be an ideal case where you would use the monitor. To gain the access, but everything can be operated remotely if desired, or completely isolated if the need be.
And Mike, just a question about the users. So you expect them to work at like currently they have access at gate level, or do they also program at the pulse level using?
Oh yes, using pulse level certainly, but this is a 6 qubit at the current moment, but it can be used as a means of being an introduction to quantum experimentation, and that allows you to get the first level of access to doing more complex operations. And qubit control is actually supported by our software stack, and we have built on top of that a number of routines using the OPX and quantum machines interface to provide levels of gate control that we have enabled to do much more complex algorithms.
Thank you very much, Mike. This is really a great pleasure for us here at APS in Anaheim to see the control hardware of quantum machines like driving such an exciting experiment, and to see the maturity of this product, which you basically just shipped here, and it just works, I would say, out of the rack.
Yes.
So thank you very much.
Well, thank you very much.